theorem number 3 is the Gram-Schmidt theorem. So, theorem 3 Gram-Schmidt theorem. This is a theorem which we saw in the previous few videos. We saw some questions based on this theorem, and in this video we will see the proof of this theorem. In fact, we did list out the steps in one of the previous videos, so we will see that in detail in this video. So let us first state the Gram-Schmidt theorem. So the Gram-Schmidt theorem says that given a linearly independent basis, we can form linear combinations of the basis vectors to obtain an orthonormal basis. So this is the Gram-Schmidt theorem. We have seen this in a few videos, in a few of the previous videos. So let us focus on the proof in this one. So let us start with a given set of basis vectors, so which need not be orthonormal. So let us denote our basis vectors in the Dirac notation as follows. So let us say we have a set of linearly independent bases given by 1, 2, 3 and so on and so forth, written in Roman numerals. So the first vector of the orthonormal basis would be given by taking the first vector of the starting basis of the old basis, which may not be orthonormal. So we take that first vector and then we normalize it by its length. So I is the length, 1, this is the length of the first vector. So let us just clarify over here that our Roman numerals are used to denote old basis, the one we start with, and this need not be this is basically not orthogonal or orthonormal. We are trying to make this orthonormal. So Roman numerals meaning this kind of vectors. whereas when we are using numbers, meaning of this form, this is new basis obtained from Gram-Schmidt, and these are orthonormal vectors, so this forms orthonormal basis. So this is the notation that we are using. So the first vector of this orthonormal basis obtained from Gram-Schmidt is given as follows, and clearly we can see that this has unit magnitude. If we find out its length, if we take its inner product with itself, then we get the following. This is nothing but 1. Now, how do we get the second vector? So, for the second vector, let us take the second vector and subtract its projection along the first vector. So, this is taking the second vector of the old basis and subtracting its projection along the first vector. Now, clearly, this vector that we have just formed by this subtraction is orthogonal to the first one. We can see that by finding the inner product with the first vector. So, let us check the inner product. Now, this is equal to 1. We saw that here. So, this is nothing but equal to 0. So, that means 1 and 2 prime are orthogonal. To make it orthonormal, we need to rescale this 2 prime vector by its own length. So that will give us the second vector. So this will have unit magnitude, making it orthonormal to the first vector. So we have got our second vector. Now what do we do to get the third vector? For the third vector, consider the following. Take the third vector from the old basis, subtract from it the projection along the first vector, as well as subtract from it the projection along the second vector. Now, this 3 prime vector that we have is going to be orthogonal to both 1 and 2, and we can clearly see that. Let us try and work that out. Let us see its inner product or projection. Sorry, its inner product on the first and the second one. So we are finding the inner product with the first vector. Now clearly this is 1 because we have it of unit magnitude, and 1 or 2 are orthogonal or orthonormal to each other, so this one is 0. Sorry, I missed out one term over here. Let me rewrite it. So magnitude of one of the first vector in the new basis vectors that we have obtained from Gram-Schmidt, this 1 written in the numbers is equal to 1, and then 1 and 2 of the new basis is orthogonal, so that this gives us this inner product as 0. So we obtain which is nothing but 0. So this means that 1 and 3 prime are orthogonal. Similarly, let us take the inner product with the second vector. So again, since 1 and 2 of the new bases from Gram-Schmidt are orthogonal, so this inner product is 0. 2 has unit magnitude, we saw it here, we normalized it to unity, so this has unit magnitude, this is 1, which finally gives us again 0, which means 2 and 3 prime are also orthogonal. Now to get a unit magnitude vector, we simply scale it. So we'll get the third vector by scaling 3 prime with its norm. So this gives us unit magnitude. And it is orthonormal to both 1 and 2. Now we will continue this process. So by continuing this process, we mean that take the nth basis vector from the old basis, then subtract its projections along the newly obtained n-1 basis vectors to subtract the projections along the newly obtained n-1 basis vectors from itself, and then normalize it. So see here, for example, if we look at this third vector, how we obtained it. We took the third vector from the old basis, subtracted its projection along the first vector from the new basis, and also subtracted its projection along the new vector along the new second vector. And then once we got this, we normalized it to get a unit magnitude orthonormal basis vector. So we will continue this process to get the orthonormal basis vectors that we wanted. Now the important point to note over here is that we need to start with linearly independent basis vectors to be able to follow this procedure and arrive at n linearly independent orthonormal basis vectors. If we do not start with linearly independent basis vectors, then at some point, let's say at this 2 prime or 3 prime or maybe 4 prime, or at some point we will see that that particular linear combination of vectors turns out to be 0. So that will stop the process over there. If we arrive at 0 or the null vector, the process will stop over there. So we need linear independence of the original old basis to start with. It is a prerequisite for this Gram-Schmidt orthonormalization process to work. So we have proved this Gram-Schmidt orthonormalization process where our new vectors, it's basically mathematical construction to obtain orthonormal basis vectors. So our new vectors are given by this process, and then this process is important. This is how we will obtain it. So this is the entire process for Gram-Schmidt orthonormalization, and this process basically forms the proof of the Gram-Schmidt theorem, since we are able to provide a method, a step-by-step logical method of obtaining linear combinations of basis vectors to get the orthonormal basis.